Okay. So today we will be, so yesterday we have already discussed about the types of data, the measurements, the variables. Today moving ahead, also we tested for the assumptions of normality. Now moving ahead, we will be moving on to the testing of hypotheses. But before moving on to the testing of hypotheses, I would like to know from the participants uh, what is an hypothesis? Just a generic definition of a hypothesis. Any one of you, please.
Hypothesis is basically an assumption, sir. Assumption about what we are testing.
Know from where these assumptions are coming. Now we must.
These assumptions are coming from basically the research, tentative research objectives that we have formed
Is it coming
based on
from
the
the?
gaps. These are again coming from gaps of
Okay.
our literature review.
Okay. Yeah, and the gaps are coming from literature review.
Yes, sir.
So you can assume anything only when you know about it. Are you getting my point?
Yes, sir.
So assumptions always comes from your initial observations. And when it comes to research, the initial observations could be your hypothesis, could be whatever you have observed or read, and then you draw the assumption. For example, when apple fell on the ground before Newton, so it was an observation by him, and probably, probably what I assume, two things might have come to his mind: why this apple is falling towards the ground, and why it is not going upwards, or why it is not staying still after being detached from the tree. What is that thing that is causing that apple to fall towards the ground was his question. And to answer that question, he has drawn some assumptions. So these assumptions are what we call in today word, in the research word, the hypothesis, which are drawn from the literature or the past work or what we know from our initial observations. So whenever you are framing a hypothesis, again, don't frame a hypothesis based out of thin air. Please formulate a hypothesis based on your initial observation of the data, or if you are doing some ethnographic research, then your initial observation while interacting with the people or your target population, or the literature review that you have done so far. To what, towards what they are directing to. These, your assumptions should be based on these things. Otherwise, if you are making assumptions out of thin air, it will be very hard for you to either prove or disapprove, accept or reject that hypothesis. The first thing. Second thing is hypotheses are of two types. Is this visible? Visible?
Yes, sir.
So there is the unidirectional, or sometimes we also call it as non-directional. Non-directional, or sometimes we often call it as, very often we call it as one-tailed hypothesis. Second is bidirectional or filtered. Can any one of you tell me the difference between these two? The non-directional or the bidirectional hypothesis, or the one-tailed or the two-tailed hypothesis?
Unidirectional basically talks about conformity of one situation.
Okay. So when you are sure that this is going
Yes.
to happen,
Yes.
Then you frame a one-tailed hypothesis or unidirectional
Yes.
hypothesis.
That means you know that the error is lying on one side only.
Yeah, means this
Then the
is
error
bound.
is.
You know that this is bound to happen. Okay,
Hmm. Hmm.
if there is a cause, definitely this will be the effect. You know,
Yes.
and how you
Yes.
know? You know because you have a past experience of it, or you have done a thorough literature review. Then only you are forming a one-tailed hypothesis. Let's say I have to drive a 10-kilometer distance and I'm driving at a speed of 100 kilometers per hour, right? There is no traffic on the road. Then it's sure to happen that if I consistently drive at a speed of 100 kilometers per hour, I will reach my destination within 10 minutes. That's bound to happen. This calculation we all do in our mind every day when we commute to our office, right? If I leave by this time, given this much of traffic, I will reach by this time. Don't we do that?
Yes, sir.
We are sure about it. But sometimes we fail to factor in the traffic signal, the amount of traffic that will be available. In that situation, we are not sure whether we will reach or won't reach. Or somebody is driving very fast. There might be assumption that he will reach well on time, or he might also meet an accident. Sorry, right? Either of these two things will happen. So when you are very sure that okay, this phenomena is going to happen, or if there is a cause X, the effect Y is certainly going to happen, then we formulate one-tailed hypothesis. And we call it a unidirectional hypothesis. When we are not sure, when we say either this will happen or this will not happen, I am not sure, then we formulate two-tailed hypothesis. One is known as the H naught, another one is known as the H1, the null and the alternate. So in most of the papers, you might have been seeing this one. You know that this is going to happen. And in some of the papers or the old school of thought, that either this will happen or this will not happen, the null or the alternate. Now, can anybody differentiate between the null and the alternate? What is the null hypothesis? Is it always a negative statement?
No, sir. It is not a negative statement, sir. Null hypothesis is always favoring the assumption. Alternate hypothesis will oppose it.
Opposite of what?
Opposes the null hypothesis. If null hypothesis says there is no difference between weights of male and female, null hypothesis says there is a difference, but it will not tell you
Fine,
surely whether it is more or less.
fine. Alternate will tell you that okay, we are going against the null, right? Alternate will always be a statement that will be against your null hypothesis. But from where will you derive your null hypothesis? First, because you have to derive your null hypothesis. Based on null, you will derive your alternate, but from where will you derive your null hypothesis?
Literature.
From the literature. So most of the people feel that if I'm writing there is no significant difference, there is no significant effect, or something which is negative is the null hypothesis. Sorry, that is not the case. Null hypothesis is a negative statement, but not a negative statement in its own. It's negation of the existing theory, right? So let's say if many studies confirm that attendance is positively linked to placement. Placement. But class attendance is not positively linked. campus placement of the students. So in that case, my null hypothesis will be that first I want to negate this. Because if I'm saying yes, I agree. Because it has a negative, if it has to be a negative statement, then it can be the same statement that yes, class attendance has nothing to do with campus placement. If I'm framing that and then I'm agreeing to this point, then what is the point in testing this? So first thing, I will negate this. I don't accept this. Okay, I'm not sure. So first I will negate this hypothesis or this finding. So my null hypothesis here, what I want to make clear is that null hypothesis is not necessarily always a negative statement. It should be the negation of the theory that you are testing. So the theory is the relationship between the class attendance and campus placement, where many studies have developed a theory that class attendance has no positive relationship to the campus placement. There means campus placement is independent of the class attendance. But if I, in the initial step, agree to this point, then there is no point in testing a hypothesis. So what I will do, I'll negate this, and my null hypothesis is the class attendance is positively linked to. I will negate this. No, I'm not. In my sample, this is not going to be the case. In my sample, the class attendance is positively linked to campus placement. And then since I'm not sure, so I have alternate statement also, which will be the same. Now you see my alternate hypothesis is a negative statement. It is in line with the existing theory. When you are negating the existing theory just for the purpose of cross-checking, it is your null hypothesis. And when you make, because a null hypothesis in, because here you are not sure, you are not making a non-directional or one-tailed hypothesis, you are making a two-tailed hypothesis. So you will make one alternate also, which will say that class attendance is positively linked to campus placement, and then you will test this null against its alternate. Please remember, alternate is never tested against the null, rather null is tested against the alternate. And for this coming to be true, P should be non-significant. The probability of occurrence should be non-significant. Non-significant. That is, P should be greater than 0.05 if you have put your confidence interval at the level of 95%. If 99% in scientific studies, then it will be 0.01 or 1%. And for this coming to be true, P should be significant. Means P is less than 0.05, and then only you can reject, because if P is less than 0.05, then reject the null and accept the alternate, that is the thumb. On what basis we do? We do it on the basis of central limit theorem or the normality. So under a normal distribution curve, you can see it ranges, yesterday only I have talked about that it ranges from mu minus 3 standard deviation, that is mean minus 3 standard deviation, to mean plus 3 standard deviation, where our confidence interval lies between mean minus 2 standard deviation to mean plus 2 standard deviation, and whatever lies between mean minus 3 standard deviation and mean minus 2 standard deviation, or mean plus 2 standard deviation and mean plus 3 standard deviation is our error zone, or the uh, that 5% whatever I'm talking about. Right? Is this clear? I hope everybody knows about it. Is that clear?
Yes, sir.
Now, where the problem is that based on our data, we accept or reject a null hypothesis, right? But sometimes we do errors, and these could be either type 1 error or type 2 error. So type 1 error states rejecting a null hypothesis that stands true in the population, and it is also known as the false positive. Type 2 error is where we fail to reject a null hypothesis that stands false in the population. For example, you see here, there is a female, means your actual values and your predicted values are true, then that is known as true positive, means that's correct. If your actual values and predictor values are not matching, then that is known as a false positive. Similarly, if your predicted value is negative but the actual value is positive, means you are predicting something that doesn't, you are predicting something. See, in first case you are predicting something and that stands true in the population, it's correct. You are predicting something that stands false in the population, you are doing type 1 error, false positive. You are unable to predict something which is true in the population, you are doing false negative, which is again type 2 error. And if you are unable to predict something which also does not stands true in the population, then you are performing a true negative. So these true positive and true negatives are the actual measurements, and false positive and false negatives are the false measurements in the hypothesis test. So always we should try to avoid or minimize these false positive and false negative. Where false positive is the type 1 error, means you are rejecting a null hypothesis that stands true in the population. You are in, if you see this example, the doctor is predicting a male to be pregnant, which is false, which is not correct, right? Here, a female could be pregnant, but a doctor is saying that no, you are not, which could be a false negative. Or other example, you can take a person who is having symptoms of COVID, but he goes undetected for COVID. That is the false negative. Means you are failing to reject a null hypothesis that stands false in the population. Whereas rejecting a null hypothesis, sorry, a person is having all the symptoms of COVID, but and if he is having a symptoms of COVID, that means he might be COVID positive, but you have rejected it. And you are testing a person over and over again who doesn't have any symptoms of COVID, then again you are doing type 2 error. So based on the data, if you are rejecting or accepting a null hypothesis, or if you are rejecting a null hypothesis, accepting an alternate one, or doing vice versa, please cross-validate with this matrix. This is known as confusion matrix. So you take all the true positives from the frequency distribution, all the false positive, all the false negative, all the true negatives, and weed out these false positives and false negatives. If the sum of false positive and false negative is more than the sum of true positive and true negative, then your finding is wrong. If the sum of false negative and false positive is less than the sum of true positive and true negatives, then your hypothesis test is correct. Otherwise, you are ending up in doing the type 1 or the type 2 error. So whenever you are doing a hypothesis test, please cross-validate your hypothesis test with a confusion matrix or a contingency table. What you have predicted initially and what you are finding actually. It will give you the number of true positives, false negative, true negatives. And please remember, false positive and false negatives are the errors in the hypothesis test. True positive and true negatives are the correctness. So if more false positives and false negatives are there as compared to true positive and true negatives, your hypothesis test is not correct. You are doing, if false positives are more, then you are doing type 1 error. If false negatives are more, you are doing a type 2 error. Is it clear? Is that clear? The first thing that you should keep in mind while doing a hypothesis test. Can I have can I have a confirmation from the audience? It is correct or it is
Yes,
okay,
sir.
or should I repeat it again? Okay, just to make sure. Now, suppose if you are finding that you are doing type 1 and type 2 error, then how to minimize it? Because always it cannot be that P is less than alpha, you are rejecting a null hypothesis, you are correct. It could be due, you are rejecting a null hypothesis, but it is not the actual situation. You are doing type 1 error. You are failing to reject a null hypothesis. That is, you are accepting an alternate hypothesis based on P is greater than alpha 0.05. You are saying null hypothesis we are unable to reject. So this is our result. Now, whether your result is correct or not, might be it is subject to type 2 error. So please cross check through this confusion matrix. And if you are getting this error, how to avoid it? So if you want to avoid type 1 error, please increase your confidence interval from 95% to 96%, 97%, or 98, or up to 99%. You can increase it. That means you are elongating your curve, okay, your confidence interval, and decreasing the error level. Right? If you are in doing type 2 error, which is more dangerous than type 1, right? So always we try to minimize type 2 error. Type 1 error, if you can minimize, fine. Otherwise, type 2 error is a big problem which should be avoided, because if you are minimizing type 2 error, you are increasing the power of the hypothesis test. It is also known as the sensitivity. So if I say type 1 error is denoted by alpha, type 2 type 1 error, and type 2 error is denoted by beta. Right? So type 1 error, I told already, a person being tested again and again for diabetes or COVID, though he is not having the COVID. Type 2 error is a situation where a person is having COVID but goes undetected. Now, which one is the big problem? A person who is not having COVID is being tested again and again is not a problem. But somebody who is having a COVID goes undetected. He will spread that disease among others. Or somebody having a diabetes goes undetected for diabetes. It will create a serious problem. Similarly, in hypothesis test, type 2 error or this beta creates the bigger problem. So this should be avoided. So if you are decreasing type 2 error, then you are increasing the power of a test. Power of hypothesis test, also known as sensitivity of the test, is equal to 1 minus this beta. So if beta is decreasing, that is type 2 error is decreasing, the power of the hypothesis test will increase. Means the cases of, you have to, in any case, decrease the cases of false negatives. Also, you should try to decrease the case of false positive, which you can decrease by increasing your confidence interval. But this you can decrease by taking correct samples and accurately test applying accurate test. This is the first thing that you should keep in mind. So first thing, based on your literature, make a directional or a non-directional hypothesis. It is always a better idea. Might be you are very sure about something bound to happen, but there might be some studies which are contradicting it, and you didn't got a chance to go through those studies, or somewhere you missed out on those studies. And since you missed out, you are saying that whatever I have studied, on the basis of that, I'm very sure that this is bound to happen. But that might not be the case. You end up in doing these errors type 1 or type 2. So always a better situation is that create a bidirectional or two-tailed hypothesis and test whether your hypothesis lies beyond that median point or the central point, to which direction it lies, whether the null hypothesis will be accepted or whether the alternate hypothesis are accepted. First thing. Then the second thing that you should do is to check for the type 1 error and type 2 error. That whatever you have concluded, isn't it having any type 1 or type 2 error? If it is having type 1 error, decrease your, increase your confidence interval. If it is having more of a type 2 error, which is much serious problem, then please again reconsidering your target respondents, whether your target respondents are correct respondents or not. Because let's say I want to know which car is better, the Audi or the BMW. I'm asking a common person, which one is better? He will answer me a random. Somebody will answer BMW, somebody will answer Audi. It is their perception. It is not the correct value. It is their perception which they have borrowed from somebody else. They heard their friends who are saying that Audi is better. So they are also saying Audi is better. Chances might be their friends also don't have any experience of Audi, but somewhere they also have heard. So see, perceived perceptions are rotating. So your target respondent should be a person who either owns both the car or at least have taken a test drive of the Audi and BMW. Then only they can give you a comparative feedback whether BMW is better or the Audi is better. I'm into many of the WhatsApp group. Most often people used to send questionnaire that kindly fill this questionnaire. Now they want to study the consumer behavior or consumer psychology. One interesting I found that somebody wanted to study the CSR activities in MSMEs, and and that fellow has floated the questionnaire in a WhatsApp group comprising of academicians. Then I responded to that fellow that we are not the correct respondent. Your correct respondent should be, because if we are giving our feedback, if we are filling your responses, there is a high chance that you will end up in doing type 2 error. We are not the correct respondents. Correct respondents are those people who are the employees of those MSMEs, and in that also more particular people who are involved in implementing CSR activities within an MSME setup. So those people will be the correct respondents. So please avoid this fallacy. Please avoid this practice of handing out your questionnaire to everybody whom you see that he is easily approachable. Sending on a WhatsApp group or sending on a Facebook. No, please, you will end up in getting wrong responses. Most often, for the sake of our convenience, we hand our questionnaires to our junior colleagues, to our students. No, where the problem will be, they are having a pressure to fill this questionnaire. So without reading your questionnaire, without reading this statement, it will be 111, 222, 333, 444. Your data is highly skewed. And again, when you will test the hypothesis based on that data again, you will end up in doing the type 2 error. So choose your respondents very cautiously to avoid this type 2 error, and keep your confidence interval to the maximum that you can. However, in social science humanities studies, we keep it at the level of 95%. In clinical trials, we keep it to the level of 99%. In agricultural studies, in we keep it to the level of 90%, because 10% margin of error is there, because agricultural activities basically depends on some other factors like weather and the knowledge of the farmer and all these things. So there are some set rules, but yes, you can increase or decrease this. But the more you increase the confidence interval, there are high chances that you are lowering the chances of doing type 1 error. The more cautiously you choose your target respondent, there is a high chance that you are decreasing the type 2 error and hence increasing the power of a hypothesis test. Now, the third thing that is need to be kept in mind is whatever you are finding from your hypothesis in the population, because always whenever we do a hypothesis test or any of the test, we do it on a sample. How much effect will it have on a population? So let's say I have taken a sample of males and females, and based on my hypothesis test, based on my data, I reached at a conclusion that females like pink color more as compared to males. Sorry, I don't have any gender. I'm not trying to make any gender biasness or comment. Just for example, that females like vibrant colors or females like pink color as compared to males. This is what I have drawn from my sample. How much it will, and I had made a hypothesis, I tested it and found that yes, this is true, that females have affinity, more affinity towards pink color. But this is from my sample. To what level this will stand true in the population? If I include each and every female and male from my population, will this stand true? And to what level will this stand true? That can be known by the effect size. So normally the effect size is calculated by either by R. So if you are doing a t-test, the value of this R will be the, where is that square root? So for that purpose, I'll just write square root SQRT of, let's say you are doing a t-test, SQRT of t square, the t value, and we will calculate it, I'll show you, upon t square plus degree of freedom. Okay. Or in simple terms, if you are having independent t-test or pair t-test, if you are doing, then you can calculate coherence D. Coherence D, which is equal to mean, because you are doing two, you are comparing two means, x1 minus x2, the mean values, upon the standard deviation. This will give you a value of effect size. If effect size is the 2.2, that means E effect 3 to 0.5, moderate effect, greater than 0.5. So these things are needed to be kept in mind. First, how we are deriving our hypothesis. It should not be on our whims and fancies. It should be grounded. It should be derived from a well-grounded theory, existing literatures, and better practices to make a two-tailed hypothesis. Then after hypothesis test, try to check that you are not doing the type 1 or type 2 error. And however, in any case, try to reduce this type 2 error and ultimately check the effect size. Let's say you have taken a sample where you have more females as compared to males in your sample, and you are saying that yes, from my study, it is found that females tends to like pink color more. But when given the entire population, does it stand true? To what level? That you can calculate by the effect size. How much effect size it is having in the overall population, your results. So that can be calculated either by the R value, which is the square root of the, if you are doing a t-test of the t square upon t square plus degree of freedom, or you can calculate simply the coherence d, because you are comparing two means, the mean score of the males minus mean score of females upon the standard deviation, or two different situations, a controlled group and experimental group. So the mean differences of them and the standard deviation of the controlled group. If you are doing ANOVA, we will do all this. In case of ANOVA, this R can be calculated by, first you will see, when you do ANOVA, you get the value SSM and SST. I'll show you where is that value SSM and SST. So this SSM is, let me put it in capitals, SSM and SST. These two values you will get in ANOVA. So this SSM is the between group effects, and this SST is total amount of values. Total amount of values. So R square value is equal to SSM upon SST. So R will be equal to square root of SSM upon SST. SSM and SST, that is between group effect and total amount of variance you will get when you will compute ANOVA. So if you are doing ANOVA or t-test, how much it will stand, means how much effect it will have in the population, the results that you are deriving, that has to be calculated by using either the R value or the coherence D value. Is this clear?
Would you, Dr. Sir, would you like to elaborate on this degree of freedom? Though, of course, it is there in the formula. Could you kindly expand on this and what effect it has or implication it has for effect size?
You want me to explain the degree of?
Yeah, the degree of, because it is appearing square root of t square divided by t square plus df. I believe
Yes,
that is
yes.
that is in bracket, right?
Hmm.
Yeah, that's in the denominator. So
Yes,
how does df affect this entire?
yes, yes,
Yeah.
yes. So degree of freedom does not only affects the entire this result. In any statistics, it is very important.
Yes.
Okay.
Mm.
So degree of freedom is basically it is the number of values uh, which are free to vary, right?
Okay. Mm.
So if I take let's say a t-test, right?
Okay.
Then the degree of freedom in a t-test will be, because if you take one sample t-test where you are comparing a population mean versus a sample,
Okay.
right? So you have only two means,
Mm.
and there is no different groups. In
Okay.
that case, your degree of freedom will become n minus 1, means total number of
Right.
observations minus 1.
That's right. Right.
So similarly, if you have two groups,
Mhm.
right, then degree of freedom will become n minus 2. That means that out of all the observations, only the observations on these two groups that you have created, they are free to vary, other are bound to be stationary.
Mhm. Mhm. Okay.
Is that clear?
Yeah, that's fine. But then you had also pointed out, let's say, you took the example of
Or,
males
or,
and females. Yeah.
or I will give one better example for degree of freedom, right?
Mhm.
Let's say there is a data set of numbers 3,
Hmm.
8,
Hmm.
5, 4.
Okay.
Okay. Now, if I'm saying that the average of these numbers, okay, I'm saying there are 5 numbers, okay,
Okay.
5 values or 5 data points,
Okay.
and their average value
Hmm.
or the mean value, you can say, okay,
Yeah.
has to be or is 6.
Okay.
Now, these are 4 data points, okay.
Yes.
For the mean value coming to be 6, what should be the next value?
Well, you have to, the sum has to come to 30. So you can divide this. It's already 9 and 11, so 20. So between the remaining two data points, the sum
It
should be
has to
10.
be exactly 10.
Yeah, that's right. Five. If it is 5 data points, yes, fine. It has to
So,
be 10. Yes.
so the degree of freedom in this case is 4, right?
Okay, because total number of data points minus 1, n minus 1.
Either by this way you can say, or if you want to understand the degree of freedom till the you have 4 data points, 3, 8, 5, 4. This
Okay.
data point is free to vary. The moment you bring the 10 here,
Uh,
its mean value is bound to be 6.
that's it.
Now it is bound to be 6. So till the 4 data points, you can put any value, right?
Hmm.
But the
Hmm.
moment you are putting 10 and
Hmm.
fixing the average value to 6, that
Then,
means now your mean value is now fixed, right?
yes.
Either by that way you can say this is the degree of freedom, that
Hmm.
till 4 data points, your
Hmm.
data is free to vary. But the moment you bring in the 5th data point,
Hmm.
correct? Your
Yes.
data cannot vary. Its value has to be 6.
That's the mean has to be 6.
Yeah.
Yeah, that's
So
okay.
now it has become stationary. Now you can't change any values.
Right,
Can
right.
you change any values? You
No,
cannot. The moment you will change, your mean value will change.
thank you.
I hope the degree of freedom concept is clear.
Yes, please. Thank you.
Yeah. So normally the sample size -1 is the degree of freedom in one sample t-test. In independent or two sample t-test, it is n-2. Then in ANOVA, the number of groups, you will have 2 degrees of freedom. So degree of freedom essentially means till the data points, your data are free to vary. So like 3854, you can put any number in between. You can change 5 to 6 or 7 or any, means you can change all these values. The moment you brought in 10 and said that the mean is 6, now these all are fixed. You cannot change any values. So till these 4 values, the data is free to vary. After the 5th value, your data cannot vary, right?
Please. That's right. Thank you.
So that is the basic definition of degree of freedom, and it is always important for any statistical test. So the maximum number of logically independent values are known as the degree of freedom. Anyone having confusion? And sir, I thank you for raising a very pertinent question. Nobody asked this question, what is degree of freedom? So it's very important to understand what is the degree of freedom.
Yes. Thank you very much. Yes.
So the mean, degree of freedom, standard deviations. These three are basic computations in any of the statistics. Yes, sir. You were having a second question also. Can I have that question?
No, that's okay. That's okay. Fine. Yeah.
Okay.
No, I'm sorry. Yes.
Yes, sir. Next question.
Sorry, you had talked about, let's say mix of males and females in gender. So
Hmm.
you took that example that they prefer pink color
Hmm.
thing. Now that means there is some inconsistency in terms of proportion of females and males,
In
right?
the sample,
Yeah,
it could
in
be.
the sample, in the sample.
Yes, yes, yes.
And this particular inference you had drawn uh,
From the sample.
from the sample, yes, from the sample, and whether that affects your hypothesis or type 1, type 2 errors. My question was around that actually.
Sir, So first we need to make that confusion matrix to see whether we are doing type 1 or type 2 error or not.
Okay.
Second thing, see, we are deriving this assumption from, or we are arriving at this conclusion from our sample.
Yes.
To what level this sample will stand true in the entire population? It cannot be the case that all females will, in the population will prefer pink. Can it
Yes.
be the case?
May not.
No.
May not. Yes.
Right? So to what level this will stand true in the population, that can be calculated by this effect size. That
Okay.
if we want to generalize this result in the population, this is what we miss out. From the sample, we report our result, but we don't report what is the effect size, which is very important in a hypothesis test, because you have tested your hypothesis on some sample. There could be inconsistency in the sample. The same sample cannot stand true throughout the population. 100% cannot be true, right? So to what level it will be true, that can be calculated by effect size. That given if you generalize this result in the population, to what level your hypothesis that you have arrived upon will be true in the entire population.
So, which means the effect size needs to be on the weak
Calculate.
side. On the weak side, yeah. Once whatever you calculate, it is preferable to have a
Sir,
weak
no,
effect,
sir, it should have a high effect
high
size.
effect. Okay.
Yeah. Sir, let's say if it is zero point 0.2 or less than that, then we can say that whatever we have derived is only restricted to our sample, because in population only 20% it will have effect. Okay.
Okay.
If it is between 3.3 and 0.5, means almost moderate effect, 50%, up to 50% is a moderate effect,
Right.
right?
Hmm.
Our hypothesis will stand true to the level of 50%, let's say if it is 0.5. If it is greater than 0.5, then we can say high effect. Means this can be highly generalizable to the entire population.
All right. So it is in relation to the sample size to the population.
Yes, 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 yes. Because
Effect size is in relation to that actually.
yes, yes, yes.
That's it.
Because every study we do, what we do, we just take a sample, and our end result, our end motive is to generalize that result to the population.
Absolutely.
So we need to tell that to what level it can be generalized, and
Good.
that can be done only by the effect
Effect
size.
size. Wonderful.
Yeah.
Wonderful.
In case of t-test,
Yes.
in
Okay.
case of comparisons, in case of regression, I'll tell you, when we'll be doing regression, we'll be getting that R value there also.
Okay.
Okay, that will tell that to what level you can predict your Y based on X.
Okay.
But till mean comparison, t-test, ANOVA and all, this coherence D or this R value that I have told you to calculate either through square root, in case of t-test, square root of t square upon t square plus df, or the coherence D, that is difference of both the means upon standard deviation. In case of ANOVA, the square root of SSM and SST. This will help you to find out this effect size, and this effect size will tell you to what level your hypothesis stands true in the population.
And I'm sorry, I'm stepping a little forward and I'm taking everybody's time, but all these are built in the SPSS software.
Sir, no, sir. These two things, these has to be calculated manually.
Okay.
Yeah.
Thank you.
But my motive is not only to restrict the audience only to the SPSS functionality. They should understand what goes beyond these statistics.
Wonderful.
And where we miss out when we report our results, because we have done a very good study, we have reported everything, and wondering that why our paper has got rejected.
Okay.
Because few things we are missing out.
Right.
Because whether your results are generalizable or not, that can be only told by this effect size.
Wonderful.
Whether your hypothesis is correct or not, that can only be tested through type 1 and type 2 error. That's why we make a confusion matrix. So all these things we should keep in mind.
Thank you.
Yeah. So this was the basics of hypothesis test. Now moving on to the hypothesis test, and our first hypothesis test is a one sample t-test. So in one sample t-test, what we do, the situation is that we have only one variable. We don't have a dependent or the independent variable. We have a test value and a variable. The variable we have calculated in our sample, and we have a standardized test value. That means we already know or we assume a value. Let's say I want to calculate the mean height of the students in my class. Already I have assumed that the mean height of the students in the class will be, let's say, 165 centimeters. Now I will collect the data from my sample and will test whether the mean height is equal to 165, less than 165, or more than 165. So what I'm trying to basically do, I'm trying to test the theory against the existing theory. There is a theory in a population, already study has been done. I want to replicate the same study in my sample and want to see that whether the study that I am doing on my sample is in line with the study that has already been done in the population or not. For that purpose, I can use one sample t-test. And second, if I want to know that whether my sample is the true representative of the population or not, then in that case also I can do one sample t-test. Here, there is no dependent. Please keep in mind, there is no dependent variable, no independent variable. You only have a variable, which you have, and the values to those variables you have collected from your sample. You are have the motive either to test that whether the mean values of the sample data is as same as already tested population data, or it is different, first thing, or you want to know whether my sample is the true population of mean, a true representative of mean or not, or whether it is deviating from it. Is this point clear?
Yes, please.
So, so if you go with the first line in my slide, the one sample t-test determines whether the sample mean is statistically different from the known or hypothesized population mean or not, right? So it is used to test the existing theory in the population. Let's say that a study has been done in the US, which states that all people who are age 20 and above have a, I'll show you the example. So then I'll come to the data point. Now let's take this problem example. Now, according to the Center of Disease Control, the mean height of adult age 20 and older is about 66.5 inches. So they have already conducted a study on all adult age 20 and above, and they have concluded that all adults age 20 and above are having a mean height of 66.5 inches. Now I have also collected data of the height of my sample, and I want to test that whether from my sample this height, the mean height of the data is as same as that of the finding of the CDC, or whether it is different. First thing, or whether my sample is the true representative of that population or not. So if my aim is to test that, then I will use one sample t-test. Is the problem situation clear?
Yes, please. Yes, please.
Others may have a from others.
Yes, sir, clear.
Okay. So means already you know something. You are assuming that this is going to happen, and then you are going to test whether this will happen in your sample or not. So I already that I have given you one example, right? That if somebody is driving at a speed of 100 kilometers per hour, reaching a distance of 10 kilometers in 10 minutes. Now you have also done the same thing, and you want to test whether you will be able to reach in 10 minutes or not. Means whether the sample will be the true representative of the population on that particular population estimate or parameter which you want to measure. Now here there are some data requirements. for doing t-test. So this first thing is that this makes it a perfect candidate for one sample t-test, where you have a test value and you want to test that test values coming from the population. You have calculated data on from your sample and you want to test that whether the data from your sample is different from that population mean or not. This makes it a perfect case of one sample t-test. But when can you perform one sample t-test? These things should be met. These are the data requirements for doing one sample t-test. So the test variable should be continuous. The value that you have assumed or the value that has been derived from the population should be continuous. That is metric, means it is taken on an interval or ratio level. As in our case, the mean height 66.5 inches was the ratio measurement. If it is not a ratio measurement, then you cannot perform this one sample t-test. Then scores on the test variable should be independent. Means if you have 10 people, you are measuring their height. Suppose you have measured the height of 4 people and it is coming out to be 62 inches. Then you cannot say that the 6th, 7th, 8th, and 9th one will also be having 62 inches. You have to measure each of the values independently. Means all observations should be independent. Okay. Data should be randomly drawn from the population, because I already said whenever you want to generalize the result from a sample to the population, then ideally you should do the random sampling. Your data should be normally distributed, and homogeneity of variance, since you don't have the groups here, so no need of homogeneity of variance. But yes, outlier should not be there, and sample should be means normally distributed. In that case, your hypothesis will be two-tailed, because you are not sure what is going to come in your from your sample. So H naught will be mu is equal to X. That is, there is no significant difference between the population mean and the sample mean, where the mu is the population mean and X or X bar is the sample mean. So population mean already you are having 66.5 inches. Sample mean you are going to calculate from your sample. And if you are saying that there exists no significant difference between the sample mean and the population mean, that simply means that the both means are equal. Means mu is equal to X. If you are saying, if you are having assumption that there exists a significant difference, see, there is a difference between the word difference and significant difference. There could be difference between the means, but if it is not significant, then it is of no value. It should be statistically significant. That means in any case, the p should be less than 0.05. Then only there is a statistical significance. Means it should lie in your confidence interval. So if you are saying that there is no statistical significant difference between both the means, that means both means are equal. Mu is equal to X bar. If you are saying that there exists a significant difference between both the means, the population mean and the sample mean, that simply translates to that mu is not equal to X. That is, the population mean is not equal to sample mean. If they are not equal, then only there will be a significant difference among them. If they are equal, then there won't be any significant difference. So you can either write that there exists no significant difference, or mu is equal to X bar, or you can write there exists a significant difference, or mu is not equal to X bar. Is that clear? Yes.
Yes, please.
Yeah.
I'm okay with it.
So the moment you are saying no significant difference means you are saying both the values are same. If you are saying there is a significant difference, that means both values are not same. So this creates a little bit of confusion, that when we say there is no significant difference, why we say mu is equal to X? Why we don't say it's not equal? See, when you are saying no significant difference, that will only happen when both the means are equal. When both means are not equal, then only you can say there is no significant difference. So you can write your hypothesis either in the form of a statement or in the form of a equation like this. Or you can also write that mu minus x bar is equal to 0 and mu minus x bar is not equal to 0. Null hypothesis can also be written as mu minus x bar is equal to 0, because if both are equal, their difference will be equal to 0. And or mu minus x bar is not equal to 0. That means if they are different, then their difference will not be equal to 0. Like this also you can write. Or you can write mu is equal to x is equal to 66.5, where mu was 66.5 in our case. So just let's see our problem statements. See. So the CDC says that if any adult is age 20 and above, then their mean height will be 66.5 inches. Now we have collected some data and let's test in our sample whether the mean height from our sample is different from this data or not. So we can formulate the null hypothesis like the x height will be equal to will be equal to mu height, means sample height will be equal to population height, means there exists no significant difference between both the height, or sample height is equal to mu height, which is equal to 66.5, where mu height is the population mean height. Or we can write alternate hypothesis that x height is not equal to mu height, where mu height is equal to 66.5, or we are trying to say that our mean height will not be equal to 66.5, means it will differ from the mean height as proposed by CDC. So since we are having only one variable, height, we have a test value drawn from sample, the mean height of the population, and we want to test that in our sample. Our sample also having the same mean height or it is different. So this is the problem statement. I hope you understood the problem statement. Now should I move on to the calculation part?
Yes, sir.
Okay. Now, please open the file. Sample dataset.sav. I have already shared all this data with you people. So you can see that height is given from our sample, and we want to test whether this sample height is same as the mean height or it is different. So our null hypothesis says that both heights are equal. That means there exists no significant difference between our this sample height and the population height, that is 66.5 inches as proposed by CDC. And alternate hypothesis says that there exists a significant difference between both the heights. So for testing this, we will do one sample t-test. So analyze, compare means one sample t-test. And we will take the height variable here. What should be the test value? Anyone? Against which value we are comparing this? Our mean height from the sample.
66.5.
Against 66.5.
66.5.
Yes, from the population. In the options, if nothing, only 95% confidence interval, click on OK. Now see. What is the mean height coming from our sample?
68.03.
And what was the mean height from the population?
66.5.
66.53.
So there is a difference.
Yes, sir.
Whether that difference is significant or not, you can see through this p value. P is less than 0.05. So it is different. Now, how to report it? We cannot simply write that P is less than 0.05, so reject null hypothesis. You have to elaborate on this. So from the one sample, First, you have to write why you perform one sample t-test. From one sample t-test, it was found that t value at the degree of freedom 407. You have to report this because if you see the table value of t at the degree of 407 and at the particular p value, you will find the t value to coming to be this. So t at the degree of freedom 407 is equal to 5.810. At this value, if you see in the t table, because previously we used to calculate all this in Excel and then calculate, and we used to have a t table and then see that what at what particular degree of freedom, what is the p value coming, what is the t value coming. But this is here in SPSS calculated, or everything is calculated over here. So at this value, p is less than 0.05. So null hypothesis, we accepted or rejected?
Rejected.
Is rejected. And what was our null hypothesis? That there existed no significant difference. Means x bar is equal to mu. So null hypothesis is rejected. From this result, we can infer that there is a significant difference. Why we are writing significant? Because this is significant at 95% confidence interval. There exists a significant difference between the sample mean height and the population mean height. First thing, in brackets, if you want, you can write that mu. Here, since on the keyboard I don't have the option to write mu, so I'm just writing mu. Or so let me take from this one. I'll take from here. Mu is not equal to x bar. Is not equal to x bar. In population, you have to write everything. I was found to be 6.5. Yes, whereas the sample mean height was found to be 68.03 inches. 03 inches. This difference stands significant at 95% confidence interval. To the total result. Now, to what level this will stand true in your population? If you generalize the mean height of your sample in the population, for that you have to calculate the effect size. So effect size R is equal to square root of e square on e square e to the power 2 t square plus df square root of this entire. Let's see if I could make it right to see. You can write size R equal to square root of t square upon t square plus degree of freedom, which will be equal to, now if you see the table, t is 5.810, so 5.810, 5.810, 33.7561, 33.7561 plus degree of freedom. Degree of freedom is equal to 407 plus 407 is equal to upon this upon 440 and 7561 is equal to 33.7561 upon 440.7561 is equal to 0.076 square root of 0.076 will be 0.27. So the effect size is 0.27 or 27%. So whatever you have founded mean height from the sample, that will be applicable to your population. That's from where you have drawn the sample, only moderately. Is that clear? So we have reported the t-wire test that okay, this was found, null hypothesis was rejected. The mean height was found to be 68.03 inches in the sample. It was 66.5 inches in the case of population. It stands statistically significant at 95% confidence interval. And whatever we found as a mean height in our case from the sample, it is it has a moderate effect, or it is only having a small representation, or moderate, only 27% representation of the entire population from where the data has been drawn. Is that clear?
Sir, can you elaborate on the value T, sir?
This value?
Yes, sir. Like what is T exactly and how it is significant?
See, t value is a particular value when you have performed one sample t test. It is the value at a value of t test, one sample t test at a particular degree of freedom, right?
Okay.
Okay. Now, how this value is significant? This is significant because p is less than 0.005. See,
Okay.
p is coming to be 0.000.
Yes, sir.
Okay. So first thing you have to report that what is the value of t at a particular degree of freedom. If you take the t table, then at a particular degree of freedom, you will find this. Let me show if I can get t table. We used to do in old school of thought. Now it's all calculated. I don't know how much clear it will be. So if you see the T table, then you'll find actually. Now at 0.05, okay,
Yes, sir.
at the degree of freedom, what was our degree of freedom?
407.
407. That exhaustive table is not given. It is only 100, then suddenly it is given 1000. But if you will see from the extensive table at 407, okay, it will come to be the same value that we have got. Okay.
Oh, okay, sir. Okay, sir.
So that have already been computed by your software. Okay.
Okay, sir.
And at that degree of freedom, okay, so what we see, a particular degree of freedom and at a particular confidence interval. Our confidence interval was 95%, so significant level was 0.05, right? So between 0.05 to 0.10, at a degree of freedom 407, you will find the t value coming to be this from the table, which is automatically calculated by the software. Okay.
Okay, sir.
So, and this value is significant. That means there exists a significant difference between our means. See, already the means are different. We got 66.5. Here from sample, we are getting 68.03. Already they are different. The mean difference is 1.53. But whether this difference is significant or not, this difference will be is significant because P is less than 0.05. Hence, we are rejecting a null hypothesis.
Yes, sir.
Is that clear?
Yes, sir, it's clear. Thank you, sir. Actually, why I asked this question is I come
Mhm.
from an engineering background and all this statistics is new to me. So I really don't know why T value was taken. So now I know that it has a history and it is taken from a table.
I
So
understand.
these,
I understand.
yes, yes,
See, simply you can write P is less than 0.05, so null hypothesis is rejected and there exists a significant difference. But unless
yes,
you don't write that, why at this particular degree of this particular P value, which is less than 0.05, and at a particular degree of freedom, what is your T value, you should not miss your results are incomplete, right?
yes, sir. That's why I just wanted a holistic understanding of what is really P and everything.
So
Thank you.
most of the people they simply report P is less than 0.05, null hypothesis rejected. No, you should write the complete result. Whatever is given in the table, please elaborate everything. It should be like that even if a layman is studying your paper or the article, they could understand what you want to say. And
Yes.
then it's always a good idea to calculate the effect size. That whatever you found from your sample, how much it is representative of the population, only 27%. Not the entire population is having a height of 68.03. Okay, only 27% of the population will have a mean height of 68.03. Is that clear?
Yes, sir.
Okay. Can we
Actually,
take?
yeah,
Yes.
actually in engineering, we are pretty sure about our, about our figures, etc. But here in statistics, because since you are comparing sample and population, so
Hmm.
95% means, it talks about confidence level. Can you say confidently that your whatever you observed in your sample is reflected in the population? So that is the level of significance. Actually. So there's
See, sir,
some amount of, yeah. So,
this is social science,
yeah,
and
I know.
when it comes to pure science, then your confidence interval goes to the level of 99%.
Absolutely, absolutely. That's where it is. And I come from engineering background as well as subsequently management. So therefore, I can appreciate the difference between how you interpret data in physical sciences as well as in social science
But
versus social sciences.
but method will be the same. Only thing will
Absolutely,
be
yes.
that here your confidence interval will go to 99%.
Absolutely, absolutely. You can't.
Otherwise, let's say you have taken you are doing some chemical reaction test and you want and you say that okay, if we mix two reagents or let's say if you come from physics, you are saying that if at a particular place the value of gravity will be 9.8 meter per second square, whether it will be 9.8 meter per second square at all places on the earth,
Hmm,
to some places it will vary,
hmm,
but it won't vary much. You cannot say that you can keep the error level to 5%.
Absolutely.
Only you can say, okay, 99% will be the confidence. A little bit of variation might happen. That is only to a level of 1%. But
Sir,
if you want to compare, the method will remain the same.
Absolutely.
yes. Sir,
Yeah.
just a follow-up question. Can we change the
Yes.
significance level test while analyzing the data in SPSS
Yes,
like you
yes,
said?
yes, yes,
Okay.
yes, yes, yes. I'll show you the step. See, you are going to analyze this compare means one sample t-test. Here in options, you can change this to
Okay.
99%.
Okay. Thank you, sir.
Right? By default, it's 95% because this software is meant for social sciences basically. Now, if you will see, this P is coming to be 0.000, but here your confidence interval, see, now this lower and upper bound have changed because confidence interval is at now 95%.
Yes, sir.
Okay. I hope this is clear now.
Yes, sir.
Okay. Can we take a 2 minutes break, please?
You more than deserve it.
Yes, it's fine, only 2 minutes, sir.
Yeah, thank you.
So let's resume the session.
Yes, sir.
Okay. Now, second situation is that you have a dependent variable and one independent variable. Again, I'm talking of univariate statistics. Means you have one dependent and one independent variable. Already I have told you the concept of dependent and the independent variable. Only thing is that your independent variable is categorical in nature. Dependent is continuous, that is taken on an interval or ratio scale, and the independent variable is categorical, and that too it is divided into two categories. If this makes it a case of two sample t-test. If these two categories are mutually exclusive of each other, means coming from two different populations like male and female, or like studious and non-studious students, means two different populations mutually exclusive of each other, means one is not affecting the other, both have different attributes. Then, and you want to test that whether there exists a significant difference between these two groups of independent samples or not, then we go for independent sample t-test. So the situation is one dependent variable, one independent variable divided into two categories. These two categories are mutually exclusive of each other. So if I take the example of science, let's say you want to test the effect of a medicine, right? So to one group, you have given the actual medicine. Let's say somebody is having fever. You want to check that if a person is given paracetamol tablets and one person who is given a placebo means just a fake drug, not paracetamol, some capsule having no drug at all, will it have, because now you have created two groups mutually exclusive of each other. To one you are giving the treatment, to another you are giving no treatment. So to whom you are given the treatment is the experimental group, to whom you are giving no treatment is the controlled group. So if this is the situation, or the groups are coming from two different populations showing two different attributes like male and female. In social sciences, humanities, management, perception of males and females towards a particular brand of car, of course, it might be different. Towards perfume, it might be different. In science, the control and the experimental group means, please remember, you don't have two independent variables. You have only one independent variable, but the independent variable is divided into category, and that too into two categories. And again, these two categories are mutually exclusive of each other. Then this case makes it a case of independent t-test. Since it is a case of independent t-test and the categories are mutually exclusive of each other, right? So in that case, you have to check also for the homogeneity of variance, because the effect or the change or the variance that you want to measure should be exhibited by both the groups. If it is not exhibited by both the groups or the variance is not equal, then there is a problem. You cannot perform the independent t-test. So today I have shown you a decision tree. Let me come to that decision tree. So this was the situation. Yeah. So this was the situation. Means you have two groups, k is equal to 2 and mutually exclusive of each other. Now, if your outcome variable is categorical, then fine, move on to the non-parametric equivalent, that is Mann-Whitney test. If your categorical, see, your independent variable will be categorical, outcome variable is continuous or metric, then test for normality, then homogeneity. So the important thing is after normality, you should test for homogeneity of variance. This is also known as homoscedasticity. What is homogeneity of variance? Means both of the groups should show the same level of change because you are trying to see the effect on both the groups. So the effect should be there on both the groups. I show you the graph. Yes, this is population 1, population 2. Here you can see the variance is small and steep. Here the variance is elongated. So there is no equal variance. Both should be of the same. The pattern should be the same. Then equal variances are there. That means homogeneity of variance or homoscedasticity is there. Otherwise, if you see these cases, there is no homogeneity of variance or a case of heteroscedasticity is there. So for independent t-test, both the groups should show equal effect on the parameter that you are trying to measure. If they are not showing equal effect, then there is no homogeneity of variance and independent t-test cannot be applied. Thanks to SPSS, it gives you two results in independent t-test. Please remember when to do independent t-test, when you have one dependent and one independent variable. Your independent variable is categorical divided into two categories. Your dependent variable is continuous and the categories are mutually exclusive of each other. Then you will test whether these are coming from two different populations, whether the population means on that outcome variable are same or different, and whether homogeneity of variance is there or not. If there is no homogeneity of variance, then ideally you should not apply independent t-test. It was very difficult. But SPSS gives you two results. When equal variances are assumed, means when it is assumed that there is a homogeneity of variance, and when equal variances are not assumed, when it is assumed that there is no homogeneity of variance. So if there is no homogeneity of variance, still you want to do, and other assumptions are met, and still you want to do independent t-test, from SPSS you can do it, but then you have to report the statistics of equal variances not equal. I'll show you how. First, let me show you the problem. And to apply, clear? When it is applied, when you want to find the statistical difference between means of two groups, statistical difference between the means of two different interventions, so that two different interventions will change the characteristics of the categories, statistical difference between means of two change scores, then in all these cases we apply independent t-test. Your data requirement should be that the dependent variable should be continuous, that is interval or ratio, and independent variable is categorical and is in two or more groups. If it is more than two groups, then ideally we apply ANOVA. Till two groups, we apply independent sample t-test. And cases should have values on both the dependent and independent variable. Means the number of observations on dependent variable should be same as the number of cases on independent variables. Means it cannot be that you have 200 observations of independent variable and 180 observations of dependent variable. No, both have to be 200. Means cases should have values on both dependent and independent variable. There should be independence of the observations. one observation should not affect the other. It is case in every statistic. Otherwise, it will lead to inaccurate p-values. Data should be collected randomly, normally distributed. Homogeneity of variance should be there. That is homoscedasticity. Means variances should be distributed across both the groups. There should be no data. Of variance already I have explained. Now here, hypothesis will be, since you have now population means, you don't have a sample mean and population mean, you have two population mean. These two populations are the two categories of your independent variables. Independent variable data is coming from two populations which is mutually exclusive of each other. So you are saying there is no statistical significant difference between both the means. That is, mu1 is equal to mu2. Both population means are equal. Or alternate hypothesis is that there is just a significant difference between both the population means. That means mu1 is not equal to mu2, or both the population means are not equal. Or you can also write mu1 minus mu2 is equal to 0 in case of null hypothesis. In case of alternate hypothesis, you can write mu1 is not equal to, or mu1 minus mu2 is not equal to 0 because they are different. That's why their difference will be not equal to 0. Then also, since homogeneity you have to test, so you have to make a hypothesis for Levin's test for homogeneity of variances or equality of variance. So the null hypothesis is that standard deviation 1 of the first sample is not equal to standard deviation of the second sample. Sorry, null hypothesis will be that standard deviation of the first sample is equal to standard deviation of the second sample. That means the population variance of group 1 and 2 are equal, means there is a homogeneity of variance. If there is a homogeneity of variance, then variance 1 minus variance 2. See, standard deviation square is the variance. So variance 1 minus variance 2 is equal to 0. That means if they will be equal, then only it is 0. And alternate is that standard, variance 1 is, and the difference of variance 1 and variance 2 is not equal to 0. That means that they are not equal. The population variances are not equal. So in Levin's, for homogeneity of variance, the hypothesis will be that there is no, the null hypothesis is that equal variances are there. The alternate hypothesis is that equal variances are not there. So if there are equal variances, means variance 1 minus variance 2 will be equal to 0. If there is no equal variance, that means variance 1 will differ from variance 2, and means variance 1 means variance of population 1. Variance 2 means variance of population 2. If they are not equal, then their difference will be not equal to 0. Means the first case is equal variances are there, second case is equal variances are not there. So now let's, is that clear till now? Is it clear?
Yes, sir.
Yes, sir.
So apart from making the hypothesis of the independent t-test, you have to also make the hypothesis of variances, whether equal variances are assumed or not. So null hypothesis says that equal variances are there. That means both the variances of both the populations will be equal, and alternate says that equal variances are not assumed. That means the variance 1 of population 1 will not be equal to variance of population 2, or their difference will not be equal to 0. Now, in our sample data set, if you see this sample data set, so Students were reported their typical time to run a mile and whether or not they were an athlete. So we want to know if the average time to run a mile distance is different for athlete versus non-athlete. Now here you see our dependent variable is time taken to run 1 mile distance. This time is a interval variable, right? It is a continuous variable. Our independent variable is coming from our independent variable is the status of the students, whether they were athletes or non-athletes. Means two different groups, athlete versus non-athletes, mutually exclusive of each other. And we are interested in knowing that whether the time taken to run 1 mile distance differs between athletes and non-athletes or not. So our null hypothesis will be the mu non-athlete minus mu athlete is equal to 0. That means there exists no significant difference between the time taken by athletes and non-athletes to run the 1 mile distance. Alternate says there exists a significant difference between the athletes and non-athletes to run 1 mile distance, or you can write it like mu athlete is not equal to mu non-athlete, or you can write mu non-athlete minus mu athlete is not equal to 0. It is not equal to 0 only in the case if their mean values are different. So first alternate says there's just no significant difference. Null hypothesis says there exists a significant difference. The same can be written in the form of equation that mu non-athlete, which is our one population, minus mu athlete is equal to 0, or you can write the alternate as mu non-athlete minus mu athlete is not equal to 0. Is that clear?
Yes, sir.
Okay. So we have a time taken to run 1 mile distance, mile minute duration, which is an interval or continuous variable. We have the athletes and non-athletes. Here 0 represents non-athletes, 1 represents athletes. Two groups mutually exclusive of each other. And we want to see that whether the time taken by them is dependent on their athletic status or not. Whether athletes and non-athletes differ in the time taken to run 1 mile distance, or it is the same in our sample. So go to analyze. So first we need to see, since we have two mutually exclusive group, we need to check Levin's test of homogeneity of variance also, homoscedasticity. That means the variance of group 1, that is non-athlete, the null hypothesis, is equal to variance of athletes. Means both the variances are equal. That is our null hypothesis. Alternatives variances are not equal. First, and I already told you that for any assumption coming to be true, p values, please remember, for rejecting a null hypothesis, p should be less than 0.5. That's why when I say that for any assumption coming to be true, p should be greater than 0.5, that means we want to accept the null hypothesis. And that's why in case of assumptions, we make the null hypothesis that the assumption is met. So here we are making the assumption of null hypothesis that equal variances are there. So let's first test the Levin's test of homogeneity or homoscedasticity. Go to analyze. That option in SPSS you will find in one-way ANOVA. So compare means one-way ANOVA. Select your dependent list, that is the time taken to run 1 mile distance. Your factor, that is your groups, was athlete versus non-athlete. And here in options, you will find homogeneity of variance test. Click this. Continue. Okay. What is the p-value here? P-value,
0.
point 0.000. Is it greater than 0.05 or less than 0.05?
Less than.
So our null hypothesis will be accepted or rejected.
It is Accepted. It is not accepted. It is rejected.
That is rejected. And what was our null hypothesis?
Uh, that the population variances of group 1 and group 2 are equal.
So now it is saying that the population variance is not equal.
Yes, sir.
So there is no homogeneity of variance.
Correct.
So the assumption is violated. But now, thanks to SPSS, it gives you, if you still want to conduct independent, ideally you should not conduct independent t-test. You should go for its non-parametric equivalent, that is Mann-Whitney test. But still, if you want to do, SPSS gives you an option. So let's do first analyze, compare means, independent sample t-test. Our test variable was the dependent variable. Time taken to run 1 mile distance, right? Okay.
Yes, sir.
And our grouping variable was athlete. Here you have to define groups. So group 1 is 0, non-athletes, group 2 is 1, coded as 0 and 1. Continue. In options, you have to do nothing. Okay. Now, if you see this table, it is giving you F statistics in T statistics in case equal variances assumed and equal variances not assumed. So when we did our Levin's test for equality of variance, however, side by side, it is also giving you the Levin's value here also. But when we did initially, what we found that equal variances were not there, isn't it?
Yes, sir.
So we will report the results from equal variances not assumed. So now our results will change here. What we will say, since equal variances were not assumed, so T as the degree of freedom, now you will take this one. So if you round it off to the next decimal, 316, rather than this one, you will take this degree of freedom. Equal to 15.057. 47. And this P is less than 0.05. So null hypothesis is rejected. From this, we can infer that there exists a significant difference in the athletes and the non-athletes who run 1 mile distance. In every type of study, you can apply this. In science, it is widely applied when you have two different experiments. What are the results of those experiments? In social science management, when you have two different group of consumers, when you have two different group of employees, when you have two different companies showing different this financial performance, then everywhere it is applicable. I'm taking one example of athlete and non. So that there exists a significant difference between the athletes and non-athletes to run 1 mile distance. The time taken by the athletes was, if you see this table, what is the mean value for athletes? That is 6 was 6 minutes, 1 seconds, while time taken by non-athletes was 9 minutes, 6 seconds. The mean difference was 2 minutes 14 seconds, or 15, you can say, 2 minutes 15 seconds. So finally, it can be concluded that athletes took 2 minutes 15 seconds less than non-athletes who run 1 mile distance. Or you can write it vice versa that non-athletes took 2 minutes 15 seconds more than the athletes to run 1 mile distance. This difference is significant at 95% confidence interval. Sorry, 95% confidence interval. Now coming to effect size. Here, since you have two mean differences, so you can calculate through Cohen's d. Cohen's d is equal to the effect size can be calculated. Either you can take the t value square upon t square plus degree of freedom, and you will take this t value and take their square root, or you can simply calculate Cohen's d. So Cohen's d is the mean difference. So the mean difference is 2.15 upon standard deviation. If you see, did we get somewhere standard deviation? Here, yes. For non-athletes, because you are taking comparison of non-athletes, standard deviation is 2.1, 2.01. 2.01 is equal to, it will come out to be, so sorry, it is in seconds, so it should not be written like this. 2 minutes 15 seconds should be written as 135 seconds. On 2 minutes 1 second should be written as, standard deviation is going to be 0.02.1. Yes, it has to be 1. What is the mean value? Now the two values, this. Yes, it has to be 135 seconds upon 121 seconds is equal to, if we calculate this, 135 divided by 121. 1.11. That means 111% effect size. That means across the entire population, it is very high effect. Means in every case, athletes will always take less time as compared to non-athletes to run 1 mile distance. And this will be applicable to, if you take any population, this will be applicable because the effect size is very high, even more than 100%. Is that clear? Same if you calculate to R, if you see the t square 15.047 square will be, let's see, 15.047 into 15.047, 226.41 on this square plus degree of freedom. So plus degree of freedom is coming to be, degree of freedom is coming to be 315 upon 541 is equal to 226.41 divided by 541 0.41 or 42 or 1842. If you take the square of this, the square root of this, let me check. The square root of 0.42. Coming to be 0.64, 64.8%. So if you calculate through the generic formula, then it is coming to be 64.8%. Again, it's very high. If you are calculating using Cohen's d, then it's coming to be very high, 111%. Means in all the cases, it is having a very high effect size. Means in the entire population, in the entire population, it will be having a very high effect. Means in every case, athletes will take less time as compared to non-athletes. There will be a significant difference between athletes and non-athletes to run a distance. Is this clear?
Yes, please.
So values are coming to be little bit different by both the methods, by calculating the R or Cohen's d, but both of them are suggesting that there is a high effect size. Okay, in all the cases it will be, means athletes will always take less time as compared to non-athletes. So what your result from the sample is showing you, the same is applicable to the your population. You can generalize the results from the sample to the entire population. Now coming to one-way ANOVA. One-way ANOVA is nothing but the extension of independent t-test. If you have categories more than three, means three or more than that, means if you have mutual exclusive categories, right, and categories are two, then independent t-test. If you have three or more categories, then ANOVA, one-way ANOVA. So if I have to see here, let's see, we have three groups here: zero, non-smokers, one past smokers, and two current smokers, and time taken by them to sprint, right, to run a distance, to sprint. Whether this differs, now here you can see that we have three categories. So this is this is continuous variable, this is categorical divided into three categories. Now these three categories, if you want to calculate, if you want to see the difference, then we have to go for one-way ANOVA. So it is basically the extension of independent t-test. So one-way ANOVA, here we will take a sprint, and here we will take their smoking status. Okay, click on OK. So here you can see equal variances are assumed because it is greater than 0.05, and you can see that the value of F, if you see this, F at the degree of freedom, since you have three groups, so you will get 2 degree of freedom, 2 and 350 is equal to 9.209 at this is less than 0.05. So null hypothesis is rejected, which means that there exists a significant difference between the key levels of smokers on their sprint time, or you can also write sprint time is dependent on smoking status. Similarly, you can write there also in independent t-test that time taken to run 1 mile distance is dependent on athletic status, whether they are athlete or not athlete. So only this much you will know from this. But you won't know, because since in two groups you can know that one group is different from the other. But if you have three or more groups, how will you know that which group is different? So for that, for further exploration, we do multiple comparisons. So in the same one way ANOVA, you can find this post hoc. So there are many methods of doing multiple comparison. The most common is the Tukey method in one way ANOVA. So select this, click on OK. You will get one another table. Now please remember, 0 is non-smokers, 1 is past smokers, and 2 is current smokers. If you compare 0 and 1, non-smokers with past smokers, it is not significant, means there exists no significant difference. If you compare 0 with 2, means past smokers with current smokers, you will find there exists a significant difference. Similarly, there is in this table, there is this already we have seen, the same value you will get, no difference. Past smokers and current smokers also, there is no difference. Only difference is exhibited by non-smokers and current smokers. So based on the multiple comparisons by the method, we found that only non-smokers first from current smokers in their time. The other groups, and these do not differ. Difference is significant at 95%. If you see this multiple comparison, you can find out from the corresponding table: 0, 1, more than 0.05, no difference; 0, 2, 0.000, less than 0.05, significant difference; 1, 0, you will get the same value. When you are comparing 1 and 2, means past smokers and the current smokers, no statistical significant difference. So only statistical significant difference is between the group 0 and 2, that is the past smokers and the current smokers. Other categories of smokers does not show significant difference in their sprint time, means they have the same, almost the same sprint time, or if there is a little bit of difference among them, it's almost you can say non-significant. Okay.
Sir, can you
Yes.
show the Mann-Whitney test instead of Levin's test? Because Levin's test is not showing any, it's showing that there is a non-homogeneity of variances. So if we have to run Mann-Whitney test, how do we do
Okay.
it?
Okay. Go to analyze. Okay. And non-parametric test. Okay. Click on independent samples. Fine. Or you can do like other way also. Analyze non-parametric test, legacy dialogues, and two independent samples. And here you can select your test variable, grouping variable, and select Mann-Whitney. Okay.
Okay, sir. Okay, sir.
I'll do it for you. See, you'll get the same results. Only thing is it's a non-parametric test. So go to legacy dialogues, two independent samples. So you are saying this one, na? Smoking,
Athlete.
smoking state, no, not smoking. Athlete, right?
Yes, sir.
Define groups here 0 and 1. Continue, and mile minute duration. Okay, and here you will select man Whitney. By default, it is selected. Okay, if you want to do the non-parametric equivalent, here also you will find the P is 0.000. There exists a significant difference. Okay, and
Sure.
here you will get the mean rank for them. So you can say that the mean rank because this is ranking non-parametric test, so you can say that the mean rank for the non-smokers were 252, while as mean rank for mean rank for non-athletes were 252, mean rank for athletes were 121. So you can say that athletes took more time, non-athletes took more time as compared to athletes to run 1 mile distance. Given that, and also this is significant. Clear?
Yes, sir. Sir, and also I just wanted to confirm in the
Mhm.
one-way ANOVA test, it
Mhm.
shows the Levine's table. In that,
Mhm.
the significant is shown as 0.09 or something. So
Mhm.
that way we
Point.
considered there is a variance in homogeneity of variance is
It
present.
was greater than 0.05.
Yes, sir.
If that
Okay.
assumption is not met, then you will do a non-parametric equivalent of one-way ANOVA, which is known as Kruskal-Wallis test. Okay,
Which is known as?
Kruskal-Wallis test.
Okay, sir. Okay, sir.
Click on K independent samples. Okay, select the same like smoking status. Define the range 0, 1 to 2. Continue, and sprint time. And here Kruskal-Wallis, right? So here also you will get that there is the difference between the groups. And then based on the mean rank, you can say which of the group is different from which one. You can find that a lot of differences between group 0 and 2. Are you getting this? Hello.
Yes, sir. Yes, sir. It's clear.
Okay. So if there is no homogeneity of variance, then you can go to the non-parametric equivalent of one-way ANOVA also, which is Kruskal-Wallis test. So this is all for the day. Any more questions? Then feel free to ask.